return to yesterday's introductory bit on redox, without necessarily getting it too complicated, because I'm aware we're several people missing, and it's just makes life harder if we've got to keep reteaching. So not intending to get this way ahead at the moment, and time-wise we're okay for chemistry. So we were looking at the idea of redox. Then is that we're looking at oxidation and reduction reactions going on at the same time, and the general principle is looking at the movement of electrons. And we broke down, some of the reaction that we looked at yesterday, things that we looked at before, and trying to identify in there where electrons were moving, also where electrons were not moving, and those are the bits that we could ignore. Those were the spectator ions, the sodium and chloride in that one. And then we started doing the definitions. So we had definitions of oxidation and reduction in terms of oxygen. A bit old-fashioned, but still sometimes useful. Similarly with hydrogen, which is just the reverse, but again, sometimes useful. And then the more important bit, as far as we're concerned, is to think about oxidation and reduction in terms of electrons either being gained or lost. And of course, we then got ourselves in a slight tangle, but this always happens, looking at what's being oxidized, what's being reduced. And of course, something is oxidized by an oxidizing agent, and the oxidizing agent is reduced. Something is reduced by a reducing agent, and the reducing agent is oxidized. So we played around with that for a while, and you had some questions that sort of, I could hear people trying to explain it to each other, and that, that's where it goes wrong. You know in your head what's happening, but trying to put it in words is actually quite hard. And then we sort of got rather too close to the end for me to be able to do anything sensible with this. And so the plan for today then is really just to finish off yesterday's work in terms of working out oxidation states of certain atoms, either in an element or in an ion or in a molecule, or it doesn't matter where it is, but working out specific oxidation states or oxidation numbers, and from there we'll then be able to move on. So there's a sequence of rules to go through for working them out. There's a real similarity with the idea of valency. So if you have your pink cards with you, then you'll actually be able to work out oxidation numbers in a lot of cases just by using the pink card. And then I've got some examples for you to do, and then that will be all we need to do on this. So this is really just completing what we did yesterday. So I'm just going to dive straight in to the rules for working them out. Right, so once we've got this, you do need to refer to this when you're working them out. First of all, the oxidation number of an atom or a free element is 0. So if you've got, let's say, oxygen, O2, oxidation number 0. A metal, iron, copper, sodium, the oxidation number is 0. All right, so that's a fairly easy starting point. So, first rule, and I shall just put ON for oxidation number. Remember, it can be oxidation state, so you might sometimes see OS. But to start with then, the ON of an atom or free element is 0. So, for example, the oxidation number of nitrogen, and we tend to do it like this and write out the name of the element, nitrogen in N2. In a molecule of nitrogen, which is a free element, then it's On is 0, or On of calcium, let's say, if you've just got Ca. All right, if in a reaction, in an equation, you've literally just got the one element or a single atom represented, its oxidation number is 0. So that's an easy place to start. Needless to say, things do get a little more complex straight away. The next one, oxidation number of the ion of an element is equal to its charge. Now this is where you've then got the pink card coming in, because, for example, the oxidation of copper in Cu2+ is +2. And the oxidation number of oxygen in an oxide ion, O2-, is -2. All right, so that's where you've got that sort of ion, then the card will come in useful. So the oxidation number of the ion of an element, remember, so it's a single symbol, equals charge. So, e.g., oxidation number of copper in Cu2+, we write it for the ion, don't we, is +2. So it's it's written the other way round. And the oxidation number of oxygen in an oxide ion, which we would write O2-, is -2. All right, so valency and oxidation number are not the same, but you do find an overlap. So the numbers are the same in that sort of circumstance anyway. Obviously, when you've got polyatomic ions like sulfate or carbonate or hydrogen carbonate, then you've got something more complex. We'll come on to those. Now, third rule is that if you've got a molecule that's neutral, like water or carbon dioxide or methane or something like that, then if you add up all the oxidation numbers, you'll get 0. All right, which is fair enough. So it's the algebraic sum. So it depends how many you've got, obviously. So the algebraic sum of the oxidation numbers of the atoms. So this is a long, complicated sentence here. So the sum of the oxidation numbers of the atoms in the formula of an electrically neutral compound, so you can't have any charge on it. Is 0. And sometimes that means that you'll know some, and then it means you can work out the others. And I'll give you an example that I just happen to have here. E.g., for the one we've got here is calcium hydroxide. All right, so the algebraic bit in the description there is really referring to the fact that we've got a 2 after the bracket, so you have to multiply it all by 2 there. So we've got the sum of this is, well, for the calcium, so +2 for the calcium. I'll put it in brackets to start with. plus then 2 lots of what we've got for the OH. Now the +2 for calcium, all right, don't be confused by that. Out of that first one where I put the oxidation number of calcium is 0. That's in pure calcium. This is not pure calcium. This is calcium hydroxide. We're looking at a calcium ion, and the oxidation number of an ion is equal to its charge. Right? So we've got 2 lots of. Well, for oxygen in a compound, we can take the ion. That'll be the -2 that we had. Yep. So it's 2 lots of -2 for the oxygen. And then we need the hydrogen as well. What do you think the oxidation number of the hydrogen might be? Sorry? +1, yeah. I'll have to put the plus in for the hydrogen. All right, so what we end up with is +2, then 2 lots of -2 is -4, so we're going to have -4, and then +2 over there equals 0. All right. You could, but it's sort of, why is it? And you don't talk about the oxidation number of an ion. You see, it's the elements in the ion. So you would break it down, but eventually you would do that, yeah. There's always a shortcut somewhere. Right, you then, the next one's a little more long-winded. Let me just read this first. For convenience, more than anything else, shared electrons in covalent compounds are assigned to the element having the greater electronegativity. Now, which way does electronegativity increase on the periodic table? Is left to right or right to left? Left to right. And is it bottom to top or top to bottom? Bottom to top. The most electronegative element is? No, other corner. Fluorine's the most electronegative, yeah? And so from there you can do comparisons between any elements. So if you've got a covalent compound, you're not talking about ions, then for convenient you'd give the electrons to the one with the greater electronegativity. So an example here, in phosphorus trichloride, the phosphorus is given the positive and the chloride the negative because the chlorine is more electronegative, it's further to the right. So I'm going to give you an example, I think, where you have to work that one out, but it is literally a convenience thing because the electrons are not really moving, they're being shared, aren't they? So for convenience, shared electrons, and I'm going to use just E- for electrons because we're going to use that word so often, I think, in this. Well, it's what redox is about. So shared electrons in covalent compounds are given to the more electronegative element. I mean, if I said phosphorus trichloride and you would look on your pink card and you'd see chlorine is -1 anyway, sorry, chloride is -1. So you'd say, oh, the phosphorus must be +3, but that makes the assumption that it's ionic and that you get Cl-, and actually you don't with this. All right, so it's not the ideal one perhaps, but so oxidation number for phosphorus, phosphorus in PCl3 is +3. Right, so the chlorine is -1. All right, because the chlorine's more electronegative, the phosphorus is less electronegative. And then the final rule is another algebraic sum one, and this relates to those ions where you've got more than one atom, the polyatomic ions like sulfate, carbonate, and so on, where the sum of the oxidation numbers of all the atoms in an ion will be equivalent to the charge on the ion. And that's pretty much what you said, Pete, that, you know, for hydroxide, yes, that's -1, but there is no oxidation number for hydroxide. The oxygen and the hydrogen have got oxidation numbers, but yeah, you do end up with it being for the whole thing. So the algebraic sum of the oxidation numbers in, oh, hang on, the oxidation numbers, I should say, of, sorry, the atoms in a polyatomic ion is going to equal the charge on the ion. Now that's quite a useful one, because it can help you work out ones that you don't otherwise know. So if, for example, you have sulfate, the sulfate ion, all right, now what's the oxidation number of oxygen? -2. So 4 lots of -2 would be -8. So what must be the oxidation number of the sulfur? If the yes, +6. Yeah, because if the oxygen's actually providing -8, but we're still left with a -2 charge on there, then the sulfur must have knocked out 6 of those. Yeah. So what you have is +6 for the sulfur, plus 4 lots of -2 for the oxygen. So we've got 6 plus -8, so hence our -2. But sulfur's one that you know, it's actually got some options, and that's quite a useful one. Just to give you another example to go with that, to do it in reverse, have we got on the pink card, have you also got sulfite? SO3 2-, yeah? SO3 2-, yeah? Let's say in sulfite, SO3 2-, oxidation number of sulfur is it 6 this time? No, it's not. 4, yeah. So sulfur has different oxidation numbers. That's all right. The something for sulfur plus the 3 lots of -2 for the oxygen. Equals -2. So the oxidation number of the I mustn't put the symbol, it's got to be the sulfur. It's +4. All right. Now this is why sometimes that won't be written sulfite, and it shouldn't really be written sulfite. For the first one, the SO4 2- would normally, well, correctly really, be written sulfate 6. That's why you get those numbers in brackets. So that's sulfate 6, written like that. Whereas that one is sulfate 4. All right, so it's telling you something about the sulfur. But we still tend to call that sulfite. It just makes it easier. All right. Okay, you've got some examples to try. And what you're doing here is assigning oxidation numbers to the underlined atoms in 10 examples. And I'll give you a little while to do them, and then we'll just go through those, and then we can do something.